Welcome to Succeed e-learning app. In this video, we are going to learn the magnetic effects of electric current. Earlier, we studied what are the heating effects of electric current. Now let us study what are the magnetic effects of electric current. Magnetic field and magnetic field lines. Let us perform a small activity. Let us take a copper wire, a battery, a compass, and a plug key, and let us construct them as shown. Now let us switch on the battery. The current flows in the circuit. Now let us take the compass and place it in the vicinity of the copper wire. Now we see that the needle got deflected. So why did the needle get deflected? We know that whenever the compass is placed in a magnetic field, the needle deflects. But who created the magnetic field? Yes, the copper wire created the magnetic field around itself. Thus the needle got deflected. Thus we can conclude magnetism and electricity are somehow related. Magnetic field lines. Just like any other field, even the magnetic field has a magnitude and a direction. Let us perform a small activity. Let us take a cardboard, some iron fillings, and a bar magnet. Now let us place the board horizontally. Let us place the iron fillings on it and take a bar magnet and place it in middle of the iron fillings. Now we see that the iron fillings arrange themselves in certain pattern, and this pattern is caused by the force experienced by the iron fillings due to the magnet. Now these pattern represents the field lines around the bar magnet. Thus we conclude this is how the field is distributed around the bar magnet. We know magnetic field has both direction and magnitude. Conventionally, we take the magnetic field lines emerging from the North Pole and converging to the South Pole. Inside the magnet, the lines flow from South Pole to North Pole. Thus, we can conclude the magnetic field lines are closed paths. No two magnetic field lines meet each other. This can be concluded by a small thought process. Let us say there are two magnetic field lines touching each other, and let us place the compass on the point where they are touching. Then the compass should deflect in two directions, which is not possible. Hence we say magnetic field lines doesn't meet each other. Magnetic field due to a current carrying wire. Let us perform a small activity. Let us take a cardboard, some iron fillings, a copper wire, a battery, and connecting wires. Now let us connect them. Let us take the cardboard. Let us place the copper wire perpendicular to the cardboard and place the iron fillings on top of the cardboard. Now let us connect the battery to the copper wire. When the battery is switched on, the current flows and the iron fillings arrange themselves as a pattern. And this time the pattern is concentric circles with the wire as the center. Thus we can conclude the field lines are concentric circles around a straight current carrying conductor. In this activity, let us take the compass and place it near the wire. We observe there is some deflection. Now take the compass and place it further away from the wire. We observe the deflection decreases. Hence we can conclude that the deflection decreases when placed farther away from the wire. This simply implies the field strength is inversely proportional to the distance from the wire. Right hand thumb rule. Right hand thumb rule is used to find the direction of magnetic field. Right-hand thumb rule states that if a current carrying conductor is held in right hand such that the thumb points the direction of the current, then the curled fingers represents the direction of magnetic field. This is right-hand thumb rule. Magnetic field due to current through a circular loop. Whenever we require large amount of magnetic field, we just bend the straight wire into a circular loop and pass electricity through it. Let us see how the field is distributed around this circular loop. Now let us see the circular loop. We know that the field is inversely proportional to the distance from the wire. Now applying this to the circular loop, we see that the field is concentric circles, and the circles keep on increasing from the distance. The circles appears as a straight line when it is through the center of the circular loop. And by applying right-hand thumb rule to all the points, we see that the field lines is as shown. If we want to increase the magnetic field, we just increase the number of turns. If the number of turns is increased by n number, the magnetic field increases n times. This is possible because the current flows in the same direction in all the loops. Magnetic field due to a solenoid. A copper wire turned n number of times in a cylindrical shape is called a solenoid. Now let us see the solenoid. When we pass current through the solenoid, the magnetic field lines appears to be similar to that of a bar magnet. One end of the solenoid acts as a north pole and the other as a south pole. The lines are parallel inside the solenoid, which means they are uniform and same at all the points inside the solenoid. Solenoids are used to magnetize materials, and these materials are called electromagnets. Okay students, hope it was interesting till now. Now let us learn what is the force on a current carrying conductor placed in a magnetic field. Electric charges when placed in magnetic field experience a force. Similarly, an electric current placed in a magnetic field also experience the same force. We know that when electric charges are placed in magnetic field, they experience a force. Similarly, the conductor placed in a magnetic field also experiences the same force. Let us perform a small activity. Let us take an aluminium rod, a horse magnet, a battery, and connecting wires, and connect them as shown. Place the horse magnet such that the magnetic field is directing upwards. Now let us pass the current through the rod. The rod deflects to the left. We can see that the rod deflects to the left. This happens due to the force acting on the rod. We can observe this by changing the direction of the current in the rod. The rod deflects to the right, and hence we can say that the force is dependent on the direction of the current and the magnetic field. Are you curious why the rod deflected to the left or the right? Now let us learn why this happens. This is given by the Fleming's left-hand rule. Fleming's left-hand rule. Fleming's left-hand rule states that the thumb, point and the middle finger of your left hand placed mutually perpendicular such that the thumb points the direction of the force, the middle finger points the direction of the current, and the forefinger points the direction of the field. Electromagnetic induction, EMI. We know that a current carrying conductor experiences a force in magnetic field. Now let us reverse the case. Now let us move the magnetic field or the coil. What happens? Yes, electricity is generated, and this was discovered by Michael Faraday. Do you know how to produce electricity using a coil and a bar magnet? Now let us perform an activity and demonstrate how to produce electricity. Okay, now let us take a coil with number of turns, a bar magnet and a galvanometer. Now let us take the coil AB and connect it to the galvanometer. Let us take the north pole of the magnet and move it towards coil B. We can see a momentary deflection in the galvanometer. Now let us take back the magnet away from B. Now we can see the deflection in the galvanometer is opposite. Thus we can conclude that whenever the bar magnet is changing with respect to the coil, a current is induced in the conductor. Now let us perform the same activity by replacing the bar magnet with a current carrying conductor. Now let us take two coils, a battery and a galvanometer. Now let us connect coil 1 to the battery, coil 2 to galvanometer. When the plug key is inserted, we can see a deflection in the galvanometer. When we remove the plug key, the deflection is in the opposite direction. When there is change in electric current in coil 1, the magnetic field associated with it also changes. This affects the magnetic field around coil 2, and this induces the current in coil 2, and thus we can see the deflection in galvanometer. The process of inducing current in a coil by changing the flux in another coil is called electromagnetic induction. We know current is induced in coil 2. To find the direction of current, we use Fleming's right-hand rule. Fleming's right-hand rule. Fleming's right-hand rule states that if the thumb, point and middle finger of your right hand are placed mutually perpendicular such that the thumb points the direction of motion of the conductor, the point finger the direction of the field, then the induced current is given in the direction of your middle finger. Do you know how washing machines, fans, mixers work in your house? They convert electrical energy into mechanical energy. We know that whenever electric conductor is placed in a magnetic field, it experiences a force, and these motors run on the same principle. Electric motor. Electric motor converts electrical energy into mechanical energy. Now let us perform a working model of electric motor. For this we require a magnet, a coil, brushes, slits and a battery. The slit rings are connected to the axle from which mechanical output is drawn, and they are also connected to the brushes. The brushes in turn are connected to the battery. Let us see the working of electric motor. When the battery is connected, the current enters the rectangular coil from X. It flows from A to B and then from C to D. By applying Fleming's left-hand rule on the arm AB, the AB is pushed downwards and CD is pushed upwards, and hence the coil rotates in anti-clockwise direction. Now we can see that Q is in contact with X and P is in contact with Y. Now the direction of current is D to C, B to A. Applying the Fleming's left-hand rule, AB is pushed up and CD is pushed down. After each cycle, the current keeps changing and the axle tries to remain in anti-clockwise direction. Instead of slit rings, commuters are used. Commuters change the current after each half cycle. In practical examples, instead of magnets, we use electromagnets. Now you have learned how to construct an electric motor and how it works on Fleming's left-hand rule. Electric generator. Electric generator. We know that whenever coil is rotated in a magnetic field, electricity is produced by the principle of electromagnetic induction. Hence we can see mechanical energy is converted into electrical energy. A typical generator consists of a rectangular coil, magnets, split rings, brushes and an axle. All these components are connected. The rectangular coil is placed in between the magnets and the ends of the coil are connected to the rings and the rings are pressed up against the brushes. We earlier studied what are electric motors. Now let us study what are electric generators. Electric generators. Electric generators are the devices which convert mechanical energy into electrical energy. We know that whenever coil is rotated in a magnetic field, electricity is produced by the principle of electromagnetic induction. Similarly, electric generators work on the same principle. This is the simple model of electric generator. Hope you all understood the construction of electric generator. Come on, now let us generate electricity using the model built. Say the coil is rotating in clockwise direction. That is, AB is moving up and CD is moving down. And we can see there is an induced current in the coil. The direction of the induced current is given by Fleming's right hand rule. And thus we can say that the current is flowing from A to B and from C to D. In the external circuit, the current is flowing from B1 to B2. We can also see that there is a deflection in the galvanometer. Now after half rotation, CD is moving up and AB is moving down. Now, by using Fleming's right hand rule, the direction of the current is from D to C and B to A. And in the external circuit, it flows from B2 to B1. And there is a deflection in the galvanometer. We observe that the current is changing its direction after each half rotation. We can say that electric generator produces alternating current. Alternating current is the current which changes its direction periodically. This is how an electric generator works. We learned that electric generator produces alternating current. That is, it changes its direction periodically. Now let us differentiate direct current, alternating current. Direct current flows in one direction. Alternating current changes its direction periodically. Do you know how electricity is transmitted to your houses? The electricity from the power plant goes to the transformer, and from the transformer it is connected to your houses. The transmission is done through AC. It is just because the power loss in transmitting AC is very less when compared to DC. Domestic electric circuits. Do you know how the circuits are constructed in your houses? Now let us see how they are constructed. From the main pole, we draw two wires, the positive wire and the neutral wire, and connect it to the meter box. From the meter box, all the circuits are connected in parallel combination. It is constructed in parallel combination just because it has same voltage. Now there are two circuits in which 15 ampere current flows and 5 ampere current flows. Now observing this, you know how the circuits are constructed in your houses. By seeing the circuit, you may wonder what is the green wire doing here. Yes, the green wire is the earth wire. The earth wire is connected to the metal plate and placed deep down. The green wire absorbs the excess current and prevents the appliance from overloading. Now you got your answer. The green wire is used for earthing and it prevents overload of any appliance. Fuse. You all know what is a fuse. You also saw a fuse is used in this circuit. Do you know why? Now let us see why it is used. When there is abrupt current flowing through the circuit, the fuse breaks and it prevents the current flowing through other circuits, and it saves many appliances also. Now the fuse is used because it prevents overloading and short circuits. Overloading. Overloading happens when the neutral wire comes in contact with the positive wire. This creates an abrupt current in the appliance and makes the appliance a breakdown. Now you know why the fuses is used in all the appliances. It protects the appliance from overloading and short circuits. Let us see what we have learned so far. Magnetic field and magnetic field lines. Magnetic field due to a current carrying conductor. Right hand thumb rule. Electromagnetic induction. Electric motor. Electric generator. Fleming's left hand rule, Fleming's right hand rule, domestic electric circuits. Hope you all understood the magnetic effects of electric current. For more chapters, keep watching Succeed e-learning app.